Today on the show, we're diving into three papers that cut to the heart of modern AI: how large language models learn, scale, and adapt. We'll explore NITP, a fresh training objective that sharpens hidden representations in DeepSeek, V2, style, and other LLMs. A MindLab vision for million personal models built on trillion parameter systems like Kimi K2 and Qwen, and a new unified scaling law from Mila and Google DeepMind that aims to predict performance across model, data, and inference scales. Let's explore the first paper, NITP, Next Implicit Token Prediction for LLM Pre-training. NITP, or Next Implicit Token Prediction, is a new pre-training objective for large language models that augments standard next token prediction with dense supervision in hidden state space. The paper shows that ordinary next token prediction provides sparse, one-hot gradients that leave most latent degrees of freedom under-constrained, causing last layer representations to become anisotropic and low rank during training. NITP fixes this by asking the model to predict an implicit token, defined as the stop gradient shallow layer representation of the next token, and aligning the final hidden state to it with a cosine similarity loss plus the usual cross entropy. The key design choice is temporal shift. Predicting the next token's semantic representation works, while same position alignment collapses and hurts performance. Theoretical analysis shows that NITP adds positive curvature to the angular subspace of the loss Hessian, mitigating the semantic null space left by next token prediction. Empirically, the method scales across dense and MOE models from 0, 5B to 9B parameters, including DeepSeek, V2, style MOE backbones with roughly 2% extra training flops and zero inference overhead. On the 9B MOE model, NITP improves MMLU Pro by 5.71 points, C 3 by 6.36 points, and Common Sense QA by 4.26 points, while also raising frozen representation quality on MTEB from 39.24 to 41.56 across 25 tasks. The authors position NITP as a compute-efficient way to make pre-training shape not just token accuracy, but the geometry and transferability of internal representations. Let's explore the second paper, on the scaling of PEFT towards million personal models of trillion parameters. This MindLab paper reframes parameter-efficient fine-tuning, especially LoRa, as a mechanism for persistent local state on top of shared foundation models aiming at million personal models of trillion parameters. Its core claim is that PEFT becomes transformative only when three scaling axes reinforce each other. Scale up, where stronger shared priors make small adapters more powerful. Scale down, where the adaptive state becomes small and stable enough to learn reliably. And scale out, where many persistent adapted instances can coexist. On scale up, the authors show trillion-scale LoRa reinforcement learning on a 104T parameter sparse MOE model, Kimi K2, using GRPO-style on-policy optimization with hybrid parallelism, reducing compute and communication to about 10% of conventional full-parameter RL while preserving stable reward and task success curves. They also identify training, inference, mismatch, and routing divergence in MOE systems as new failure modes that require router replay and provenance-aware serving. On scale down, a Qwen 3.8B PPO sweep over 216 runs finds that ranks 16 and 32 are the most reliable middle regime, while ranks 1-4 retain strong best-case performance but suffer seed sensitivity. And RL native initialization, OLoRaTail, stabilizes rank 1 training and improves DeepSeek R1 Distill Qwen 1.5. B. Benchmark accuracy from 56.3% to 58.3% average, with a larger win on Qwen 3.30B, A3B Instruct, where it reaches 35.5% versus 24% for standard LoRa. On scale out, the paper introduces LoRa as memory and context learning, reports a bounded memory capacity law on dish name benchmark, and shows per-user LoRa adapters improve social simulation in OASIS and majority vote accuracy on AME24 from 0.3644 at one model to 0.4867 at 198 models. The infrastructure layer, MinT from MindLab, turns adapter identity, revisioning, and bounded residency into a deployable lifecycle for persistent personal models. Let's explore the third paper, Unified Neural Scaling Laws. Unified Neural Scaling Laws, from Mila researchers Ethan Caballero, David Kruger, and Irina Risch, with Priyank Jaini of Google DeepMind, proposes a single multivariate curve family that models deep network performance as model size, dataset size, training steps, inference steps, batch size, and hyperparameters vary together. The key novelty is a nested functional form built from multivariate, broken neural scaling laws with smooth hyperbreaks, plus explicit terms for bottlenecks, irreducible performance limits, overfitting, and non-monotonic hyperparameter effects such as learning rate and initialization scale. Unlike earlier scaling laws, such as the Kaplan and Hoffman-Chinchilla style formulas or Muning-Hoff et al. Data-constrained language model law, UNSL can represent transitions that reverse direction and does so with the same asymptotic expressivity as simpler baselines. On held-out extrapolation, it is substantially more accurate. In downstream image classification, it is the best model on 60.87% of tasks versus 21.74% for the next best form. And in language, it wins on 88.89% of tasks. Reported RMSLE drops include ImageNet bivariate extrapolation from 254 E1 for DC to 857 E3 for UNSL, and language bivariate extrapolation from 624 E2 for DC to 782 E3 for UNSL. The paper also shows the law extrapolating reinforcement learning, test time chain of thought scaling, width depth trade-offs, and sparse parity, while revealing a practical limit. Accurate forecasting past a regime change requires training data near the relevant hyperbreak. That's a wrap on today's AI paper highlights. Thanks for watching.